Assalamualaikum warahmatullahi wabarakatuh. My name is Madina binti Cipta, and this video presents my PSM2 project titled Study of Thermal Effect in Silicon Carbide Power Mosfet. This project is supervised by Dr. Faiz bin Arid. So in this video, I will explain the problem background, the methodology, the key simulation result, and also the significance of this study. Okay, look at the problem statement of this project. We all know silicon carbide MOSFET are designed at high temperature, but they are still faces some problem on their performance. One of the major issue is threshold voltage instability, which is mainly caused by interface trap and also the oxide defect at the silicon oxide interface. So this instability affect the device reliability, efficiency, and long-term performance. So making the thermal analysis very important. All right. So look at the objective of this project. Okay. First, to design a 4H silicon carbide power MOSFET using console multi-physics software. And second is to analyze the thermal effect on the device performance in terms of the current conduction, recombination effect, and defect density. I use console multi-physics to perform a detailed semiconductor simulation. So it is given to interface trap behavior. So where the trap capture and release an electron, and also the significantly affecting the threshold voltage as temperature increases. Okay, let's look at the. Okay, this is the flowchart of process flow to design the 4H silicon carbide MOSFET using console multi-physics software. So I will explain more detail of each process so you can better understand what the process of the silicon carbide semiconductor. Okay, first, this slide shows the MOSFET geometry. Okay, so we can see that the source of the body are connected to the ground, while the different voltage are applied to the key and drain to observe the device behavior under the operating condition. I assign the material, including the 4H silicon carbide for substrate, and also I also add the silicon oxide for the gate oxide. Okay, next is the semiconductor physics. In this step is the semiconductor physics, which is I setting by the doping concentration, the recombination mechanism, and the channel mobility. I apply the refined match to improve the simulation accuracy, especially near to the channel region. So finally, I add stationary study to analyze the steady state electrical and thermal behavior. And the first result I got is the electric potential. So as you can see in the animation of this video, we can see the electric potential distribution inside the MOSFET. So which help us how charge move inside the MOSFET. Okay, so this device is N-type silicon carbide MOSFET, where the electron are the majority carriers. When a positive voltage is applied to the gate terminal, an electric field is created across the outside layer. So this electric field attracts electrons toward the silicon carbide oxide interface and repels the holes away from the surface. As a result, an inversion layer of electron is formed, so which create the conducting channel between source and the drain. So from the electric potential, we can observe that the potential is the highest near the drain region. Okay, that's the result of the MOSFET behavior. So we can see the transfer characteristic graph and the output characteristic graph. Okay, this graph shows the IDVGS and IDVDS characteristic. So the device operates in three regions, which is the cutoff, linear, and saturation region, which is confirm that normal MOSFET behavior. Okay, as you can see in the above graph, we got the normal MOSFET behaviors. Okay, so the extracted the threshold voltage is at at approximately 1.2 volt, indicating a good gate control. So at high temperature, the saturation current decrease, which suggests an increase in ion kinetics. This is the result demonstrate how temperature affect the current conduction during switching. So as temperature increases, the switching become a slower and the peak drain current slightly decrease. Additionally, leakage current increases at high temperature due to high intrinsic carrier concentration in silicon carbide. As you can see, the both graph shows the channel mobility as a function of temperature. Okay, so the channel mobility decrease with increasing the temperature, mainly due to the phonon scattering, which limit carrier movement. Meanwhile, the threshold for voltage decrease as the temperature increases. So this behavior caused by enhanced carrier activation and a stronger interface rate effect at the silicon oxide interface. Next result is shows the effect of intrinsic defect concentration and trap density. So as trap density increases, the threshold for voltage shift and the channel degrades. This is covered that interface defect play a major role in the thermal instability and long-term reliability of silicon MOSFET. Okay, first the threshold voltage decreases. Okay, so this happens because higher temperature energy make it easier for carriers to form the channel, which reduce the gate voltage required to turn on the device. The carrier mobility does not change linearity with the temperature. So from the result, electron mobility reach it peaks around 250 K, while the whole mobility peak at approximately 500 K. So low operating voltage, the leakage current increases with the temperatures. This is mainly due to the reduction in threshold voltage, which allow the more carrier to flow even when the device is supposed to be in the off state. Okay, for this project, Sustainable Development Goal or SDG, as we all know SDG. So this project support SDG 7 entity by enabling the more efficient power device for renewable energy system. Now also the improve the efficiency, reduce energy loss, heat generation, and overall carbon footprint. In conclusion, increasing the temperature, reduce the threshold voltage, and affect the carrier mobility in 4A silicon carbide MOSFET. And also, a leakage current behavior depend on operating voltage and defect is only impact the device stability and reliability. For future work, experimental validation using the fabricate silicon carbide MOSFET, very recommended, and also improving the gate oxide quality and also the exploring the new dielectric stack can further the enhance the reliability and switching performance. That conclude my project presentation. Thank you very much for watching my video.